The Claisen reaction is the reaction of two esters. I'm going to show this, even though it's the same molecule, reacting as two different colors in this case. So here we have our blue molecule and our red molecule, the same molecule, but they're going to come together in the presence of sodium ethoxide. And in this reaction, we will actually get a deprotonated compound here. This reaction takes one equivalent of sodium ethoxide, and as you can see, we have this blue part coming from one molecule, and then this red piece here coming from the other molecule. After the reaction, these are usually acidified to give the proton back here. And so we'll add an equivalent of acid, which protonates this, but we can go a step further. And often, acid and water are added. This gives the proton, but this will also cleave the ester to the acid. And then if we heat this, we can affect decarboxylation of this product. Decarboxylation gives this symmetrical ketone. However, this piece here is coming from this molecule, and this piece comes completely off, and we're just left with this 2-carbon unit from this side. Let's just talk a little bit about selection of the base. So here we're showing sodium ethoxide. The first stipulation is the base cannot be NaOH. This is because esters are hydrolyzed in the presence of sodium hydroxide. So if we were trying to enolize with sodium hydroxide, instead we would get cleavage to the carboxylic acid. And here in this case, we would actually have the sodium carboxylate of the carboxylic acid. So NaOH is not an option. Our second stipulation is that the ester and the base must match. Here we have an ethyl group, and here we're using sodium ethoxide. Let's see why this is important. If we took this ester and instead used sodium methoxide, we would get attack of methoxide at the carbonyl, and we would get a switching of the ester, and so we wouldn't get the product that we were expecting. Instead, we get this, which is the product of a reaction called transesterification. So the base cannot be sodium hydroxide. The ester and the base need to be the same group. And now let's go ahead and look at the mechanism. In the first step of our mechanism, sodium ethoxide comes in and deprotonates here, forming an enolate. This enolate can attack another molecule of our starting ester. We get formation of a tetrahedral intermediate. And then this will collapse, kicking out ethoxide as a leaving group. I'm just going to redraw this to show this in the orientation here. Now, in this case, we've made a more acidic molecule. Now this hydrogen atom is flanked by these two carbonyls. So in this case, this was fairly acidic. We can make the enolate, but now this compound is very acidic, and the equilibrium is such that a ethoxide is going to deprotonate this completely. So it's very important that we show this anion forming as the final step of the mechanism. This is going to be a single-headed arrow. This is irreversible. The mechanism stops here. And this is the reason that we need a full equivalent of sodium ethoxide to make this reaction proceed. Now, this will be treated with acid. First, our anion is going to be protonated. And so we arrive at this. And now we're going to get hydrolysis of this ester group to the carboxylic acid. This can also be done by treating with NaOH, but we'll just show an acid-catalyzed mechanism since acid also cleaves esters to carboxylic acids. The oxygen, the carbonyl oxygen, becomes protonated in the presence of acid. And now this is activated for attack by water. This is charged, so we're going to deprotonate utilizing another molecule of water. And now we can protonate this and make it into a leaving group. We're still in the presence of acid, and so here we'll get protonation. And now one of these OHs can use its electron pair to kick out ethanol as the leaving group. Now we're a deprotonation away from a carboxylic acid. I'm just going to show -H plus here since I'm a little bit out of room. So water comes in and again attacks the proton, puts the lone pair back on oxygen. And now this is going to undergo decarboxylation when heated. We'll need to redraw this again to show how this occurs. So when this is heated, we're going to get an irreversible reaction happening, and this will decarboxylate. The reason that this decarboxylation can occur in a facile manner is because the Claisen gives us this beta-keto acid. And this can come up and form this cyclic intermediate. This is going to attack the proton. This will fall in, forming a molecule of CO2 and breaking this bond. And we get this cyclic array of electron movement, which is favorable. So this occurs when heated. Our molecule of CO2 bubbles out of solution, and that's what makes this irreversible. And so the CO2 is formed from this side of the molecule. And then what we're going to get is an enol. But as we know, enols love to tautomerize and give ketones. And so this is how we arrive at our symmetrically substituted ketone. The Claisen reaction will give you whatever group is here after decarboxylation in a symmetrically substituted ketone. This ester here, that can be envisioned as the product from a Claisen reaction, is an acetoacetic ester. The ester has a beta keto group, and this group can be variable. As we mentioned before, the protons here are quite acidic, and this is the reason in the Claisen reaction that we need one equivalent of sodium ethoxide to drive the reaction forward. There's a final deprotonation here. In the acetoacetic ester synthesis, we can capitalize on the acidity of these protons to introduce alkyl groups. So let's just consider the decarboxylation of a substrate like this again. What we expect is this group to convert to the carboxylic acid under acidic or basic conditions, followed by a protonation, and then heating will decarboxylate, leaving just this group. So if we decarboxylated this directly right now, we would get acetone. But say our target was something like this. We can look at this and retrosynthetically think, well, we'd actually need another group here prior to the decarboxylation to form this ketone. So the acetoacetic ester synthesis is going to allow us to make these unsymmetrically substituted ketones. We look here and see that we just need one more methyl. And so we can treat this with sodium ethoxide. This generates the enolate. And then we can treat this with, for example, methyl iodide. And the anion will attack and become alkylated. This will give this product. And now if we envision decarboxylating, converting this to a carboxylic acid and decarboxylating, cleaving this bond, that will give us the product that we want. So in this case, we're using acid in water to cleave this to the carboxylic acid, then heating, and that gives our desired product. So the acetoacetic ester synthesis gives us ketones. We're also going to look at the malonic ester synthesis. This begins with a malonic ester. So the difference between the acetoacetic ester synthesis and the malonic ester synthesis is the starting material. This is a malonic ester. It has two ester groups on it. And of course, again, these methyl groups could be variable. We could show those as ethyl or anything like that. In this case, when we envision the decarboxylation, we're going to cleave this to the carboxylic acid and one of these groups is going to come off. Now, this side will also be cleaved to a carboxylic acid. You have two esters. You're treating them with hydrolyzing conditions, so they'll both cleave. Now, one group will decarboxylate. However, the other group cannot decarboxylate. It doesn't have the assistance of the beta carbonyl in order to do so. So let's just look at slightly different cleavage conditions. Here we'll use sodium hydroxide. And this will give us the anionic form of the carboxylic acid, the carboxylate. Then we'll protonate using HCl and H2O. And finally, we'll heat this. And the product that we'll get is this carboxylic acid. Now, just as with the acetoacetic ester, we can introduce alkyl groups before this decarboxylation step and give ourselves a substituted carboxylic acid. I'm going to show this process all in one step. First, we'll treat this with sodium methoxide. Remember, to avoid transesterification, this base must match. That will generate our anion here, our enolate. Then in a second step, when that is deprotonated, we'll add ethyl bromide. Remember, this does need to be a second step. We don't want the sodium methoxide prematurely reacting with ethyl bromide and causing an elimination reaction. So we add in the sodium methoxide, allow this to deprotonate, then alkylate with the ethyl group. But we don't have to stop here. Here we showed an example where we just included one extra alkyl group. Let's go ahead and put two groups on here. There are 2 protons, and this can be deprotonated twice. So in a third step, after this alkylation, we'll treat this with sodium methoxide again and generate a new anion. And in the final step, let's alkylate with something a little different. We'll use benzyl chloride. So let's look at the product that we get from this 4-step process. So we see our new malonic ester has the ethyl group and the benzyl group introduced. This CH2 phenyl is called a benzyl group. Now let's decarboxylate. We can think about one side cleaving or the other, but it doesn't matter because we arrive at the same product. Let's just draw our squiggly line here. First, we'll treat the substrate with acid and water. And in a second step, we'll decarboxylate by heating it. Our first step gives us the dicarboxylic acid, and the second step decarboxylates just one of those. The final product that we get from this reaction is this carboxylic acid. Just to summarize, both the acetoacetic ester and malonic ester syntheses allow us to introduce alkyl groups onto substrates. The only difference with these reactions is they start with different starting materials, and the acetoacetic ester synthesis will give a ketone, and the malonic ester synthesis will give a carboxylic acid.